right, so thanks everybody to attend today's machine learning seminar. We are have a great honor and pleasure to invite Professor Romit Maulik from Penn State to give us a talk on this differentiable physics for scientific machine learning. So Romit is a assistant professor of data science in Penn State. He graduated from Oklahoma State University, and he received a lot of awards, including the Margaret Barter Fellow in the Argonne National Laboratory, and also he is a early career awarded. So I met Romit in 2022 when I just joined as a faculty in Europe, and I met him in the YouTube workshop, and he already done a lot of great work. And at that time, I thought I have to invite him to give a talk here at our university. So today, it's my pleasure to have you here. So right now, the floor is yours.
Okay, great. Okay, Kaichi, thank you so much for the invitation. Thank you everyone for the conversations this morning, and I'm really happy to talk to you, to present my work. I wish I was there in person, but I'm on paternal leave at the moment, and the program manager I have at home is my 11-month-old daughter. She's kind of very demanding. So, but hopefully another time, we'll get to meet, and we can discuss more about our work in person. So yeah, today I'll be talking about some work in differentiable physics. So Kaichi's also been doing some great work in this area. So we share a lot of synergy over here. And hopefully, I look forward to your thoughts and your comments. Please feel free to interrupt me at any moment during the presentation. Okay, so just some high-level overview, which I think I will speed through, because this audience should be quite familiar with a lot of these things. I come from a community which has done a lot of research in computer simulations or computational science or scientific computing, where the idea is that for a variety of applications, if you can set up a system of governing laws, typically in the form of a partial differential equation with some initial and boundary conditions. Here, there is an unsteady term because a lot of my applications are dynamic, but you can choose to interpret this as pseudotime, for example, for a steady state problem. And this has engendered a lot of scientific discovery, a lot of advances in many domains that touch our life on a daily basis. But there are some common bottlenecks in classical simulation-based research. For example, there may be some imprecision in what these laws actually are, and they may not be fully accurate. You may also have uncertainties in what the initial and boundary conditions may be, and frequently this is something that shows up a lot in sort of multi-scale and multi-physics applications. Your simulations may need to be really unreasonably simplified, right? So this is because you don't have infinite compute resources, you don't have a lot of time, so you to just get a simulation to completion, you may have to really make very strong assumptions about your problem. So this is kind of a common problem in many classical scientific computing research scenarios. And in contrast, in recent times, we've had a lot of success with what is called the fully data-driven approach. So I have an example over here from a paper published in ICML in 2020 from folks at Google, where a graph neural network was essentially used. I mean, if you don't know what that is, it's not really very important. But the idea was that, data, large amounts of it, of course, was used to basically model a physical process through a learnable kind of, in this case, a dynamic simulator. So a neural network would predict the evolution of the system in time in a purely data-driven manner. No equations were involved, no laws were conserved or preserved. But however, this was rather remarkable that you could get such rich physical outputs purely from a data-driven model. However, there are some challenges to using this for example, applications that demand high precision, particularly in science and engineering. Firstly, you may not have a lot of data, right? You might not have enough data to really train a fully data-driven model for your system. The data itself may be generated using scientific computing. So in some sense, you've not really you've kind of just shifted costs. You've basically had to generate lots of data using an existing simulation technique and then just stopped using it. So that reduces the attractiveness of using a data-driven model. And then finally, there are many scenarios, and arguably a classical scientific computing researcher will say this is where you really need data-driven modeling, where you don't have data at all, where your simulation workflows or your simulation platforms are not able to give you predictive performance, but then you don't have a lot of data available to really bypass computer simulations completely. Okay, so that brings me to scientific machine learning, which is a term that was coined by the Department of Energy in 2019 in a workshop report that has kind of, I'm sure Kaichi is familiar, that has kind of become ubiquitous in lots of literature and also in workshops and in conferences and proposals, of course. The idea is to hybridize the last two things that I talked about, where we try to impose some knowledge about the physics in the form of known governing equations, but we also account for the fact that data is present and can be used to inform the learning of our models. So there is this pretty popular visualization from Ben Moseley at Imperial, where a neural network was used to fit a damped pendulum with and without the application of the constraints that correspond to the damped pendulum. And you can see that when you do have data, a data-driven model is able to perform well. But when you don't have data, if you don't have any sort of physical constraints that are imposed, then you basically extrapolate and get non-physical results, right? So this encapsulates in a nutshell really the promise of SciML and physics-informed machine learning, right? Where we can impose the knowledge about the underlying data, right? So there are some challenges with this IML approach, and Kaichi also has been working on this for quite some time with some new results. But generally speaking, the most popular methods that are applied for scientific ML don't guarantee the preservation of physical laws. These are usually satisfied in a weak sense, typically by a loss function with a logmatic Lagrangian. And then you end up having challenges scaling to realistic problems. The second bullet point over here is something that I believe is very important to me personally, and I think generally the field as a whole needs to think about this a little more carefully. Fitting models is one thing, but is there something you can do that actually gives you back in the sense of scientific discovery? Can you learn something about the data that you did not know ahead of time, right? The third point over here goes back to the problems with classical scientific computing, which is, in many cases, you don't really know what the governing equations are exactly. In such cases, the constraints that you're subjecting your model to may actually end up biasing your predictions because these constraints are not right. So in such cases, how do you account for this? And then finally, this is something that I'll be talking about today. A lot of the studies that you see out there about SciML will typically not talk a lot about the objective. They will assume that it's a differentiable objective, right? A mean squared error type of formulation. But then that may not really be the physical objective, right? That might not be what you're looking at as a scientist or an engineer for your computer simulation. So in that case, what do you do, right? So these are some things that I try to think about when I come up with my my proposals for algorithm construction. So, and some of these will be reflected in the work I described today, right? Okay, so differentiable physics, which in my opinion, is a promising way to start making inroads into those four limitations I introduced in the previous slide, is in some sense as I say over here, combines the best of several worlds, right? So, firstly, so I'm from the Department of Energy, and anybody who's worked with the Department of Energy will know that there have been several decades of legacy development in solvers that have been scaled, parallelized, that have led to hundreds of PhD theses, thousands of careers, and it's basically stuff that can't get thrown away overnight, right? So there is always a good value to leveraging those developments and trying to preserve them and trying to improve them as against getting rid of them. So differentiable physics, which I'll introduce in a bit, it basically allows you to keep using those legacy developments, but it's also compatible with recent advances in ML. So operator learning, physics-informed models, diffusion models, transformers, all these remarkable advances that are coming, that are being developed, around the world nowadays. You are still able to leverage their tremendous, capabilities. And then finally, one of the most important things that differentiable physics allows is for learning from a variety of data, right? You can have data from varying modalities and fidelities. It could be numerical, experimental, sparse. And the idea is that we basically set up learning in the sense of an inverse problem formulation. So if you are able to take a machine learning algorithm, it doesn't have to be a neural network, but for this talk, let's assume it's neural networks, and we embed them within legacy solvers, right? As against throwing them away and then imposing constraints using an augmented Lagrangian. If we can actually embed them within legacy numerical solvers as if they are a part of the numerical solver, and then calibrate these in an a posteriori manner or a model consistent or an online manner where we are basically going to have a tight coupling between your machine learning algorithm and your numerically discretized PDE, then you can basically address these three positive properties. And also, I would argue, lead to scientific discovery, which I hope to convince you through the rest of this talk. Okay, so I'll start with some background work before I go into what my definition of differentiable physics is. It's also a common definition. So I work with a lot of dynamical systems. So one of the approaches that I have found very comfortable to use from the ML community is the approach of the so-called neural ordinary differential equations, or neural ODEs. So this was in some sense rediscovered in 2018 with a best paper award at NeurIPS by David Duvenot's group in Canada, but really ideas related to essentially system identification of PDs or ODs obtained after a method of lines discretization of a PD were prevalent even in the early 90s by work in the chemical engineering community by Yanis Kevrakidis. Of course, back then computational resources were not that easy to come across, so it was more an academic exercise. But recently, this has now been applied to many realistic problems because of a growing democratization of compute. So let's say you have a system of equations here given by a PDE where you do not know what the right-hand side is, right, of the PDE. So you assume that can be approximated by a neural network. But let's say you have access to some training data, which comes from time-varying snapshots of the state of the PDE. These don't have to be uniformly distributed, but for argument's sake, let's assume they are uniform. And then the whole goal is to essentially find what this right-hand side is, which basically means find what the weights and biases of this neural network are, such that your generated trajectories from this neural OD match the ground truth trajectories, right? In the sense of minimizing a mean squared error. And the system identification can be done by a couple of ways. Essentially, you have to compute the gradients of this loss function L with respect to this parameter theta. And you could do this by implementing a discretized discretized ODE solver, such as like a RK45 or TVD RK3 in a AD compatible framework like Torch or JAX. That's number one over here. Of course, in such a case, you have to pay the penalty for storing intermediate states to do automatic differentiation. So it's memory inefficient. The other approach is to essentially use a construct the adjoint of this equation in the continuous sense and then discretize the adjoint and solve backward. That would be memory efficient, but then that causes it may not be that easy to solve the adjoint because you could have numerical issues over there. So not really what we will be going into a lot of detail over this talk, but just a couple of options over here that were also explored in the original paper. Okay, so to develop the concept of differential physics, I'll start with a simple experiment, and then we'll gradually layer more complications. So I like this set of equations a lot because in some sense it parallels a lot of real world systems. So this is a set of PDEs known as the Kuromoto-Shevchinski equations. It is unsteady. It has a quadratic nonlinearity, so that leads to rich nonlinear dynamics. But then it also has this second and fourth order linearity, which leads to a like an ergodic behavior or an invariant type of behavior that is a good solver should recover, right? And I'll demonstrate this to you. So we'll also assume that the system has periodic boundary conditions, is one-dimensional, and it's discretized in the spatial dimension appropriately. In this case, let's say it's 32-dimensional. So we discretize this into 32 degrees of freedom, and we solve a system of equations that is 32-dimensional. We'll also assume that I'll talk about point 2 first, that we only have short-term history of the state evolution, right? So this is a chaotic system. So we only see short-term behavior, and we can only learn from short-term behavior. But as I mentioned, there is some rich emergent phenomena from the system. So from chaos emerges order. And so our goal is, can our machine learning method actually also capture the emergence of this order from chaos, right? So it complicates problems a little. To address this complication, we will relax one assumption about the neural OD. We will say that we assume that we have some partial knowledge of the terms of the right-hand side, right? So we don't know what the terms are, but we just know about some organization over there. For example, we believe that there should be a linear term as well as a nonlinear term on the right-hand side. This is not a strong assumption because many systems in nature, such as Navier-Stokes, for example, right? They have a linear term as well as a nonlinear term. So this is not, we don't know what the nature of that linear term and nonlinear term is. We just assume that they exist in an additive manner. So then what is our goal? Our goal is, how do we learn these equations or learn the behavior of these equations from short-term traces of data alone, right? So the idea is, okay, we want to get short-term accuracy. That's what all machine learning wants to do for a dynamical system problem. But then we also want to capture the emergence of order from chaos, right? So that's the invariant property. And the issue is we've never observed the invariant property in our training data set, correct? So how do we recover this from our trained models? Okay, so let's see what we can do with this. I still haven't come to differentiable physics, but you can see I'm gradually adding physics to my problem and differentiating through it. So to deal with this problem, we proposed something a couple of years ago called the stabilized neural ODE, right? So the idea was you stay faithful to the formulation of a regular neural ODE, but on the right-hand side, we introduce some knowledge about our system. The knowledge, you remember, we assume was that the right-hand side has a linear term and a non-linear term, which is additive in nature. So what we impose is a linear term that is learnable. So we can learn the linear term, but we also impose some structure, again coming from our best as estimate of how these systems behave. We say that the linear term is symmetric, positive, definite, and behaves like a finite difference discretization, right? Very simple. So we say, let's learn a linear term that represents a finite difference tensor, and then let's have a nonlinear term that is a standard black box neural network, right? And we learn both of these things together. This is in contrast to the standard neural OD, which I have over here, where the right-hand side is just a neural network, right? So just that's the. But other than that, nothing changes. The loss function is still short-term mean squared error that we try to optimize for, right? But we will see that by imposing this structure, we actually get some desired emergent behavior, right? Okay, so before we go into some quantitative analysis, let's train these two types of neural ODs, right? The stabilized one and the regular one, and see how they behave, right? So on the top row over here, I have data from my training data, right? So I have, and each column corresponds to short-term evolution, I believe the time step was 0.001, and long-term evolution, right? So that's going several pseudo time units into the future. The training data over here was only available for the short term, and it was generated by a spectral solver. So, like basically the best we can do in terms of ground truth for the system. The middle row over here is the neural OD, regular neural OD. So the regular neural OD, as you can see for the short term, it does all right. Eventually chaos kicks in, right? And it starts behaving in a different way. This is the standard property of chaotic systems. But you see in the long run, it's even to the visual eye, to the visual, test, you get non-physical behavior, right? Usually the neural ODs would basically blow up and give you not a number, but if you do a very thorough search of hyperparameters, maybe you can get a neural OD that stays stable in the long run, but this is still not accurate. The third column over here, the third row, sorry, over here is the what we call the fixed linear method, or the method where we cheat. Essentially, what we do is, instead of learning the linear term, we specify the exact linear term, right? So the exact linear term is basically these two guys over here. We can take like a 5-point stencil, not 3 over here. We can take a 5-point stencil and exactly specify the linear term, and then what we get out of this is the fact is a nice observation. We of course get short-term accuracy before there is a trajectory divergence. That's chaos. But in the long term, at least again to the visual norm, visual test, we are able to be physical, and there's quantitative study in a bit. And the last row is what I proposed, which we call CNN, because we use the CNN module for the linear term, but we are essentially able to recover the behavior of the fixed linear or the exact linear term. But now here the linear term is learnable as well. So we learn the linear term and the nonlinear term together, right? And if you do a little bit of quantitative assessment of the behavior of these different models, on the left-hand side is the short-term error, again, averaged over many initial conditions and evolutions. You will see that all these models behave approximately the same. They have been trained on the short-term loss. They have been optimized as much as possible in terms of hyperparameter tuning. So maybe the fixed linear is slightly better, but I wouldn't claim that, honestly. I would just say that they're all performing about the same in the short term. The error grows, as you'd imagine, for a chaotic system, and then stays about saturated for a while, right? But what you see in the long term, and this is the really cool thing about KS, there is order that emerges from this really chaotic trajectories. If you integrate Kuromoto-Shevchenski for a sufficiently long amount of time and plot a PDF of the first derivative of the state and the second derivative of the state, you get this beautiful teardrop shaped attractor, right? So you basically have this a region of high density where so it's kind of like an invariant chaotic attractor. You have this region of high density where the state basically stays more, and then you have low density as you kind of go out, and in the middle you have an island that shows up basically over here. So this island of low density. So you have high density, and then you have this ring of low density, then you have this ring again of high density, and it's really quite remarkable how such a simple system can give rise to such real beautifully complex behavior, right? Then if you check the performance of these three different trained methods, the regular neural OD, even though in the short term it does all right, in the long term does not pick up this order at all, whereas uh, both the fixed linear and the learnable linear approach are able to recover this behavior. So this, I want to impress on you how much of a like an achievement this is, because I never had knowledge about this, right? I never had knowledge about this during my training. This was actually recovered after I integrated my trained model for a very long duration into the future. And so this is um, I would say, at least an example of scientific discovery, because I did not know that there was this order that was inherent in my data set, right? Of course, there are many challenges. We have assumed that there's no noise in my data. In reality, there will be noise and so on. But towards the end of this talk, I will show you results from more complicated data sets where we can claim that this is a this is a recurring sort of property of our trained systems. So good start, right? Other things that we can get from this that also feed into the scientific discovery angle is this linear term that we learned, right? So this linear term over here that we learned, now we can do all sorts of analysis on it, right? That comes from, for example, approximate inertial manifold theory. We can look at the linear term, we can do an eigen decomposition of the linear term. And what we find, which was very exciting, is that after we were able to learn this behavior, this emergence of order from our trained linear term, then the linear term's eigen decomposition also revealed a low rank behavior. Now this tracks because for chaotic dynamical systems, especially, for example, for the Ks equations, it has been established through theoretical study that the low rank behavior of the linear term is really what leads to this emergence of order, right? So that's the whole existence of an inertial manifold onto which the trajectories kind of collapse. So over here, the fact that our machine learning method was able to learn this order that emerged from our data, but also sort of recovered this low rank structure in the linear term that it learned, was very exciting. So over here, when we did the eigen decomposition and we plotted the basically the what I'm plotting in the y-axis over here is the unsteady component of the dynamics projected onto a particular eigenvector. You saw that the vast majority of eigenvectors contain no dynamical information versus a few that did contain dynamical information. So that means that there's this low rank issue structure. If you then identify the eigenvectors that do contain information of the dynamical sense, you can actually do what I call flipping the script, which is you can identify a set of basis functions onto which you can project your neural OD and get a low dimensional model. So you can basically do an eigen decomposition of A, compute the eigenvectors that correspond to the underlying manifold or the underlying coordinate system, and then project your neural OD onto that. So over here, for example, if P is my projection matrix composed of these eigenvectors, I can multiply my neural OD, which is U state with P and its complement Q, and then I can end up with a set of equations for the resolved and unresolved variables. I can use like the approximate inertial manifold theory to essentially say that dq by, if I assume dq by dt is 0, which is a good assumption based on this information, then I can essentially close this system by imposing q equals a inverse of the orthogonal complement q of p. Details, but what I'm trying to say is that you can actually get a reduced order model of your original surrogate by identifying a system of coordinates that came to you through the joint training with dynamics, right? So, so this is the stabilized neural OD. This was published in 2023 in JCP. Happy to discuss this more, but this is an idea of how you can kind of impose physics during the training procedure itself, but in a hard form, right? So you're actually discretizing the linear term, and kind of identifying this low rank structure. Okay, so some details over here. What we are testing over here on the left hand side is basically the convergence of the invariant attractors. So this invariant measured as a density, so we can compute the difference between, say, the ground truth and these predicted models in the sense of KL divergence. So the KL divergence drops as you retain more components in the A term over here. So that also tells you that you're actually capturing the manifold accurately as you increase the number of eigenvector components. So yeah. Okay, so that was a standard neural OD, which we kind of augmented to account for the fact that our data set might be generated by a chaotic anticipative dynamical system. The connection to differentiable physics is, I mean, what we were doing is already differentiable physics, but the idea that or the definition that I or my group pursues is what happens if, the right hand side, a lot of the right hand side is learned, is known. So for example, in this example, we have this fixed linear approach where we exactly specified what the linear term is. So of course, in the KS equations, it's very easy to manually plug this into PyTorch or JAX and kind of go on from there. But let's say you're using a code where what you know about the physics is something like a complemented finite element solver. In that case, your governing laws, where you want to correct the governing laws, or you want to add the nonlinear term as f, but the existing physics r are coming from a very complicated uh, numerical solver. You basically have to construct essentially a sort of like a connection between a solver which is differentiable, and of course a neural network which is also differentiable using automatic differentiation. So in the past, we have a lot of experience with solving PDEs. And we have decided, as I mentioned previously, to embed a neural network into the right-hand side of a PD. Of course, this is problem and domain dependent, but I will explain that for specific applications in a bit. And our goal is to do online learning or a posteriori learning, right? So we basically have to solve the PD, or have to discretize the right-hand side of the PDs, add the neural network connection also in a discrete manner, perform a numerical time step update in a, using an OD integrator, and then compute a loss in the sense of trajectories, right? To enable that, we essentially use the chain rule of calculus. So if our numerical solver possesses a discrete adjoint, so there are some solvers out there that do, for example, Phoenix, which has the PETSI adjoint, then you can essentially use the chain rule of calculus to compute the gradients of the a posteriori loss with respect to the flow variables. Over here, I give you an example for Navier-Stokes. So dl by du by dp star. P star is the intermediate pressure. And then all the way back to the parameters of the neural network using basically the chain rule of calculus, right? So du star by d theta over here would perhaps come by automatic differentiation because the neural network is predicting u star given theta. But the rest would come from the discrete adjoint. So this is kind of how I've defined differentiable physics for some applications, right? So I will give you details of the software development that we have been doing in a bit. What the example that I will use going forward is related to KS, but kind of slightly more complicated. Sort of necessitates the use of like differentiable physics as I've introduced it. So we'll talk about Navier-Stokes equations. So incompressible Navier-Stokes governs the behavior of fluid flows. And in the past, one big challenge in using Navier-Stokes for really turbulent problems, or problems where this RE term on the right-hand side is very high, is that you frequently don't have enough computational resolution to resolve all the wave numbers in your solution. So it is necessary to model a correction term in the momentum equation given by the divergence of this stress tau, right? Now, in the past, people have used many empirical as well as physics-based models for tau over here. For example, people have modeled it as a so-called eddy viscosity, where they have said that, okay, this is linear in the strain rate. So the strain rate is the gradient of u with respect to x. Uh, and there have been other models out there that have also implemented nonlinear terms for this stress tensor. So our goal in this differentiable physics framework, just like the previous example for KS equations, is to not touch what we know about the physics, right? So not touch the fact that there is a nonlinearity, also that there is a pressure gradient, that there's a linearity, but really identify the correction to these terms so that our governing laws can actually get more accurate, right? So this is the physics that was missing, and we want to kind of learn that using data. The details of this formulation are not very important, but what we set up is a stress tensor that is kind of building on past literature for physics-based models. In particular, we have a linear term and a nonlinear term for the stress tensor. The nonlinear term can be learned as a set of 4 coefficients. So this is in 2 dimensions. We can also do this 3 dimensions. All these matrices become well, 3-dimensional, well, 3 by 3, and there are more coefficients. But we basically want to learn these in a spatiotemporally dynamic manner, right? So to solve this problem, we also want to kind of address the fact that for many realistic scientific computing applications, we deal with cases which are maybe benchmarks in the physics domain, but quite challenging in the computer vision or machine learning domain. So one such example is the backwards facing step over here. This is a very interesting physical phenomena where you have flow going from left to right. There are walls on the top of the bottom, but at the bottom there is essentially a step which causes the flow to separate. And if it's an unsteady problem, then you have a lot of rich structure that emerges over here at the bottom. This has many applications. For example, when you're flying, when your landing gear come down, and so on and so forth. But what is interesting about this is that it's a benchmark for fluid dynamics, right? It's not a very particularly difficult problem to solve. The discretization for this particular flow field is available from for the last 40 to 50 years. It's available at the NASA Langley repository for turbulence modeling. The geometry is well defined, but the discretization itself, if you inspect it closely, you will see that it has a few properties that kind of make it challenging for machine learning methods. For example, there's high anisotropy in the mesh. So, the points are very sparse upstream and downstream of the step, but near the step, there's this really fine structure. So it's not amenable to structured grid learning, right? So you can't use CNNs, for example. There is not a clean map to a computational domain where everything is uniform. The other thing is the data itself has, a lot of anisotropy. So certain regions of the flow field are completely boring, right? But others have a lot of advection dominated behavior. So it's a benchmark, but it helps you think about your algorithm development, in a realistic manner. And so let's go back to the idea of differential physics and the fact that we can actually set it up as an inverse problem, right? And we say that, okay, we'll impose a measurement constraint, right? So we'll say that we want to calibrate a correction to Navier-Stokes. So we want to learn what this tau tensor is, and we want to learn it globally. But we'll say that we have access to ground truth uh, at only these bold points over here downstream of the step. So the idea is that you only have partial observations of the step of the state. And the reason this is a good assumption to make is that, for example, if you're running an experiment, or if you're dealing with a real engineering device, then there are maybe certain regions which you will never have access to with measurement devices. And we'll also assume that we don't have access to a fine scale simulation as well, because we don't have the computational resources to run that. So this is an idea of an example of a multi-fidelity type of approach, right? Now, in this particular example, I am just assuming that the information at these points is available from a fine grid solver, but that is only for the proof of concept. The hope is that we can also sort of generalize this to experimental data, right? And so over here, our goal is to fix the flow physics everywhere globally, so that the error at these locations is minimized, right? So the idea is that those locations contain information about our flow field and our physics. So we will use that to fix everything everywhere. All right, just a recap of how exactly we've constructed our differentiable physics formulation. To deal with the unstructured grids, we have a graph neural network that uses multi-scale message passing. That's probably another talk, which I won't go into a lot of detail, but it addresses the issue of unstructured data on very fine meshes. We essentially set up Navier-Stokes as an observation operator in the sense of data assimilation, where if there's a quantity of interest, J, which here is coming from these observations here, then we can basically compute the adjoint of J with respect to the stress tensor, and then ultimately compute the gradient of J with respect to the parameters theta using the chain rule of calculus, right? So very briefly, just wanted to also mention the fact that we have to use geometric deep learning to address the fact that we are on unstructured meshes. again, the nice thing with GNNs or graph neural networks is that there are parallels with function approximation using linear methods, such as finite volumes or finite elements on unstructured meshes. The fact that node updates are like cell center updates and edge updates are like flux updates makes it a comfortable thing for numerical analysts to use to deal with the fact that we are actually solving for or approximating functions on very, very fine meshes with perhaps millions or billions of degrees of freedom, not in this particular case, but in other applications. We basically have to do this decomposition of meshes into successively coarse and fine scales, kind of like a geometric multigrid type of approach. It's also called the graph unit approach, where we are able to accelerate convergence of our learning by passing messages farther and closer, more quickly, right? So, but again, the subject of a different talk. Okay, so let's say I train this model and then I back out a right-hand side. How does it compare with the ground truth? Over here, the ground truth is only the finer solution that I obtain on a finer mesh. Again, I only observe data downstream of the step over here. I do not have access to anything near the step. As you can see, if I don't have a closure, of course, my model is not that good, especially near the walls. It's not that great. But if I use the machine learning closure, which is the example on the bottom, I'm able to have a lower error. This is also lower compared to these other models that I used, where I try to manually hand tune a fixed closure that is applied everywhere, right? So if for example, I went back here to my model and I specified what the C sub S is manually and not let it vary globally or temporally, I could, of course, improve the accuracy from this example, but it was not as high as a spatiotemporally dynamic value for those coefficients, right? Okay, and then if I go and plot the behavior of my solution at a particular probe over here, again, where I did not have access to data, but now that I've finished training, I can actually access the ground truth. And I was able to see that in comparison to the manually specified closures, where I've manually optimized for these coefficients, I was able to get a closer fit with the right amplitude and phase of the flow evolution. But in the long term, I was getting some essentially some phase errors as well as amplitude errors, which is actually related to the next part of the talk. What happens if you integrate for a long time into the future for such chaotic dynamic systems? You will remember. In this particular case, I just want to mention that we didn't impose any specific structure for chaotic behavior, right? So this was just a short-term trajectory-based error, right? So in terms of costs, once we've actually deployed this ML model, we saw that once we actually trained it, we saw that we were getting a speed up as compared to, let's say, the fine grid solver. But of course, in the interest of transparency, we do need time to train this, right? So training, of course, needs more optimization. We needed 6 hours on one A100, but we have parallelized this, and hopefully we can reduce the wall time for training and continue to get the same benefit during speed up, right? So that's always a problem with SciML methods, right? But what's cool about this is, the fact that in addition to fitting the trajectories downstream of the step, right? So these areas here, we've calibrated a correction everywhere, right? Globally. So we can actually inspect that correction and learn something about our physics. So for example, our model actually learned a coefficient, which actually connects to the dissipation of turbulent stresses. And we identified that to fix trajectories downstream of the step, you need to activate this correction at the step. Now, this is something that physicists know, right? Because we studied this problem for quite some time. But it was great that the machine learning model was actually able to recover this, right? That we were able to recover the fact that we actually have to learn close to the step in order to fix trajectories downstream, right? And we were able to leverage this and take this machine learning closure model and actually deploy it on problems that have similar physics. So for example, here Is flow over a smooth ramp, flow over a wall-mounted cube, flow over a Gaussian bump. Similar types of physics where you have flow over an obstacle that has separation. And what we were able to see is that the closure model was also activating its dissipation. Again, this is not fine tuning. This is not relearning. This is literally just deploying the same closure, but on a different geometry. That's where the graph neural network comes in handy because it's mesh agnostic, right? So the idea was that we are actually now able to learn across, like different geometries that share the same physics, which is ultimately the goal of many of these applications, right? I also want to note that while Phoenix is still very much an academic code, there are tools with which you can actually make this more performant. So we are collaborating with some folks at Argonne Leadership Computing Facility to scale up our example. For example, that was a 2D example, but we are setting up a 3D example now, which, as you can see, has a lot of rich structure and probably complicates the learning problem quite a bit, both in the sense of the HPC side of things as well as the learning side of things. So yeah, so but ongoing work basically. Now, there's another reason to use these embedded neural networks. Again, not enough time to go into a lot of detail, but the fact that you can actually integrate a combined machine learning model as well as a numerical solver lets you do some Taylor series analysis. Remember, numerical analysts love to use Taylor series for checking the a posteriori error of their numerical methods. And in these two references over here, actually, let me pull this aside. It was independently proven by both my group and some folks at Los Alamos and UC Santa Cruz at about the same time, approximately. We were just a few months ahead, that the a posteriori error for a closure model embedded in a PDE, discretized PDE, actually is connected to the Jacobian of the right-hand side. So the 2 norm of the Jacobian. So if F is the right-hand side, of course, fully known plus neural network, and you take the Jacobian of that with respect to whatever goes into the right-hand side, the U bar, the P, then and you take the 2 norm of that, or the Frobenius norm of the Jacobian, then you basically get this upper bound for the error. What this is telling you is that there is a possible regularization strategy for your learning, such that you can try to keep the Jacobian 2 norm down, so and get better a posteriori error, right? So this is again ignoring chaos for now, just short-term performance. But this actually shows up in some empirical evidence from Karthik Duraiswamy's group in 2018 at Michigan, where they actually used this for regularization and got improved behavior for deterministic dynamical systems, not chaotic ones. But of course, they said that they weren't able to give a rigorous explanation for it. But a few years down the line, we seem to we suspect that this is the reason why you get better performance, because you're able to use this sort of upper bound. Okay, so now the thing is, I had a lot of fun talking about this first part of the work, so I'm kind of running out of time. So I will try to speed up in the next 5 minutes and just go back to this original problem of chaotic systems. Turbulence is a classical example of that. In many such cases, we basically have time series data, but mean squared error is only meaningful in the short time sense. In the long-term sense, two trajectories may be dramatically different because they are chaotic, but both perfectly physical. Professor Chi Wang at MIT in the aero department recognized this about 10 odd years ago and proposed, well, more than 10, I guess, and proposed the least square sharding approach for computing sensitivities of chaotic systems. Probably, again, it's very difficult for me to summarize this method right now. It's very mathematically involved. But basically, it was a method that scaled poorly with respect to the number of, it was cubic with respect to the dimensionality of the state and the number of independent variables. And so, one thing that I've always been interested in is how do we compute the sensitivities of chaotic systems more efficiently? This is an example of the problem I'm talking about. Let's say we have Lorentz, and our goal is to compute the sensitivity z bar of Lorentz, so this term with respect to one parameter rho, and z bar is nothing but the time averaged behavior of this equation. If you basically plot z bar with respect to rho by just doing a brute computation, right? No computing derivatives, just plotting it. You can eyeball the derivative. It's the slope of this line essentially, right? But if you are to compute dj by d rho using AD or finite differences, any sort of a method for adjoint computation, you will get garbage gradients. This is in a nutshell the problem with chaotic dynamical systems. So if you zoom into this line over here, you will see that it is highly discontinuous, right? So that's why you can't really compute gradients properly. And this is a problem that was recognized by people in the climate dynamics community almost 25 years ago in this paper over here. What they claimed in this paper is that if you want to get useful gradients for dj by d rho, your capital T has to be a very small number, which is what everybody has been using, like for chaotic dynamical systems. If capital T is small, you get lower adjoints, or you get sensible numbers on the right hand side, but you get the wrong slope on the left hand side. So that's a plot in that paper. I highly encourage you guys to take a look, right? So, and what that basically tells you is that all the machine learning methods that have been failing for long-term performance but doing well in the short term have basically been doing this by setting this t value to be a very small number and then getting a gradient that can be used for optimization but is not the right gradient for the actual physics, right? So in that sense, one way we wanted to address this problem is we proposed a new method called the uh, multi-point strategy for adjoint sensitivity computation or chaotic sensitivity computation. The idea was to do something in between, right? Instead of going long-term and facing this problem on the right-hand side, or going short-term and converging to the wrong adjoint, the wrong value of dj by d rho, for long-term prediction, we wanted to do something in the middle, right? So we split up a long trajectory into multiple sub-windows, and then we introduce these relaxed continuity considerations at each intersection of windows. What we say is initially we want to learn the short-term behavior very accurately, right? So we basically try to behave just like a regular time series learning problem. Over time, as we do well in the short term, we also want to gradually make sure that the discontinuity at the intersection is reduced, right? And to do this, what we learn is we learn parameters for our neural OD to recover this short-term trajectory, but we also try to minimize, we also learn the initial condition for successive trajectories, right? So that's the idea over here. Short-term loss plus intermediate discontinuities with a penalty term, right? Uh, Once we implement this, we'd see that the gradients look much more smoother than when if we just use short-term loss. Now I'm running out of time, so let me just accelerate a little. We go back to the same problem for KS equations. We assume just that we have a black box right-hand side. We don't assume the linear term anymore, and we just now use an improved method for computing adjoints. When we do that, we see that, again, this is the ground truth. This is the attractor that is the concept of order. The regular neural OD either doesn't converge or gives you the wrong shape. The stabilized neural OD, because we explicitly added the low dimensional, the dissipative manifold concept in the sense of a linear term, is able to recover this island. But by using better adjoints, you do get stability, right? So you do improve on the neural OD, and you kind of start to pick up this low probability region over here. Of course, it's not as good as really adding the structure explicitly, but you see that by having better adjoints, you can actually recover the qualitative nature of order better. So that's just as an example of finding the right gradient of your objective function really does help you getting long-term performance, right? I think I will leave this slide up. This will be my second last slide probably. But another type of emergent behavior for something like the KS equations is extreme events. So what I have on this plot on the y-axis is the return period. On the x-axis is the maximum value of the state. So you can think of this as a plot that measures if the maximum value of the KS solution is 2.8, how long does it take to have that as the max again? So you can map it to the Earth's atmosphere and say that if the maximum value for the temperature over the Earth is a certain number, how many days or how many time steps until that is again true, again the max. So if it's 60 Celsius, so it's very high, of course, this takes a very long time for 60 Celsius to be the maximum temperature. So that's why these plots typically look like this in the log scale of the y-axis, right? If you look at the red line, the black line, that's the spectral solver. So that's how it generates extremes. So for an extreme value of 3, it takes, I don't know, a certain number of thousand time steps for it to come back. But if you compare these 3 different trained neural ODEs, again, there's nothing is different between them in the sense of the right-hand side. It's just an MLP, right? But by changing the optimization strategy or by adding physics, you can see a vanilla neural OD does not get the right behavior of extremes either. But by adding structure, you get closer and closer to the ground truth. Now, this is also an objective that is not differentiable, and this is also not observable from training data, right? Typically, you don't have the black line. So just more evidence that physics does help and adjoints do help. Okay, so Kaichi, how much time do I have? It's 12 over there. I don't want to overstay my welcome.
Yeah, it's about the time. Right?
It's time's up. Okay, then I will skip this last experiment, which is an Earth system experiment, and just leave this slide up and say that I'm super excited to talk to all of you about basically trying to come up with machine learning algorithms that lead to scientific discovery in various applications. Thanks again for the invite. It was a great delight to be here, and I look forward to carrying on our conversations. Yeah.
Okay, thanks for the wonderful talk. So right now the Q&A floor are open. Any question from the audience?
I think there's one in Zoom. Maybe.
Okay, so maybe we can start with
Oh yeah, there's a chat.
Chung's questions. How is the computational cost in the correction step?
That's a good question. So I can give you one for the backward facing steps. So by adding that computational cost for correction, you can assume that we basically added 0.2 seconds, you can say per time step. So there is a cost, yes, because you basically now added some extra floating point operations for computing, like a correction term. But in this case, because one good thing that I did not really mention about this problem is since a lot of the heavy lifting of your dynamics is done by the physics, which you're not really touching, right? So the neural networks that you can use in the differentiable physics formulation can be quite simple, right? See, I didn't really talk a lot about the architectures and stuff. You can get away with using pretty simple architectures. Of course, we used a GNN over here, but the GNN is pretty efficient as against something like a transformer type of architecture that's trying to learn the full dynamics, right? So it's just trying to correct. So yeah, so that's kind of the computational cost that we saw.
I see. So thanks. Thanks for the clarification.
Sure.
I'm like in the correction term. So I'm just out of our curiosity. If you are like okay with a little bit more computational overhead, I'm wondering if you can kind of like verify your correction, maybe every 100 step, or if it's not every step, like use the governing equation or something. Is that possible? Or
if it's verifiable, I mean, we would certainly like to do that, but it's just difficult to tell. So this is the problem where scientific discovery comes in, right? So this concept of closure for turbulence, people don't really know what it should look like, right? I mean, there's been a lot of controversy about what exactly to use.
Yeah.
So I wish I could verify it. There are some ways you could verify it by, for example, one thing you could try to do is you could plot what the tau looks like at the wall over here. Maybe that could be one way to verify, but even that is controversial. So we don't really know the boundary conditions for tau either. So this is really like a situation where we don't know the physics, right? So it's almost like we cannot verify it, right? So there are some things for closure. There are some things called realizability conditions. So this stress tensor, if you do an eigen decomposition of the stress tensor, then the eigenvalues and eigenvectors should have certain relationships that can be used. But then the large part of the community believes that that condition is bogus, and
Okay.
so yeah, there's still quite a lot of science that has to be discovered even after the fit over here. So but there's an opportunity now that we are kind of recovering these spatiotemporally varying values for tau, right? So yeah, perhaps we can actually learn what the right relationships are. Yeah.
Yeah. So I was thinking like this is after training, like this is the whole inference procedure. I
Yes.
guess.
Yes. Well, I
So-
mean, now our training also has inference, right? So if you think about it, like when we do online learning, we kind of initially have tau as a garbage model, right? Garbage weights. We evaluate it. We put it through our Navier-Stokes operator. We get garbage outputs, and then we backpropagate against the loss, right? So even during the training, there is a inference of the Navier-Stokes operator. So training is costly, right? Compared to, let's say, a situation where you had some ground truth data for tau. But what I'm saying over here is that in this particular example, I don't even have ground truth for tau, right? I just have observations of each of the Navier-Stokes solution, and the Navier-Stokes solution, it does not give me tau, right? So that's kind of like why it's an inverse problem.
I see.
Mhm.
Yeah. Thanks. Really
Sure,
nice.
sure.
talk. Thanks.
Thank you. Yes.
Yeah, so can you go to slide 25?
Oh, sure.
I think when you talk about the upper bound of the average, so the exponential term seems to kind of blow up very quickly, right?
Yes, that's right.
So is this due to the analysis might be suboptimal, or this is expected?
The analysis is also suboptimal. So I'm happy you asked this question. One of the things that we are trying to do on top of this is, so right now we haven't actually accounted for any spatial discretization errors. We've only done an analysis for as if we had the perfect right-hand side and we just integrated in time. I suspect this will change more. I don't know how to do it yet. I'm more an engineer than a applied mathematician. Once we incorporate spatially discretized operators for the right hand side, I suspect this analysis will change a little. But I do believe that the exponential term should show up.
Okay. And another one is slide 27.
27.
Yeah. So I'm curious, is there understanding why this happens? I mean, the very noisy and unstable kind of gradient. So
It's your classic issue with deterministic chaos, right? So if you think about like Lorentz 63, you can take two initial conditions, right? I can actually go to the schematic. You can take two initial conditions in this three-dimensional universe, and you can just have an epsilon perturbation to the first initial condition to get the second one. They will stay close for a short amount of time, but then after some time, they will completely diverge, right? They will completely diverge and go into completely different regions of this universe, right? Now, over time, they will stay on this butterfly. So over time, they will actually collapse onto this butterfly, but there's no necessity for them to be close to each other. You see, they're close to each other in the Euclidean sense. They will just be in the same region of phase space occupying this attractor. And that is in some sense why when we increase this the limit of this integral, so as we increase the amount of time which we are tracking these two positions and comparing the norm between them, that this gradient explodes. because the distance between them exponentially increases. This is a property of the underlying dynamics.
So it sounds like it's really that because the function is very, very oscillatory, and so the gradient become very, very large.
Yes, yes. So if you actually like plot this function and then zoom in expectation it's smooth, but if you zoom in, you will see that it's extremely noisy and extremely like kinky. So.
And the numerical values you got from the plot, is it by some AD or is it by adjoint method?
So in this case, I think it's by adjoint method, but you would have to look at the original. You would have to look at the original paper. I think it's adjoint method, but
this reminds me about the non-smooth problems. Current AD system is not complete for non-smooth problems. That means if you do AD on non-differentiable cases, they may give something inconsistent, depending on how you specify your function. That's one thing that probably is relevant. And another thought here is that why? I mean, if this is the case, it sounds like when people deal with this, they probably need to think about some non-smooth analysis, right? Because it's numerically it's non-smooth. Although yes, I think theoretically it's differentiable, but just because this thing changes so quickly, so that's almost like the function is non-smooth. Right? So I think some of the non-smooth analysis tools can be relevant here.
Okay, I'm not super familiar with those, so I'd really appreciate a reference to look at. Happy to keep the conversation going. Yeah.
All right. So maybe due to the time sensitive, we close the talk right now, but we can